Hello everyone, welcome to our discussion of section 2.4, where we will be talking about more techniques of finding the derivatives of functions. Now in this section, we will be talking about the product and quotient rules for finding the derivatives. In other words, if you have two functions that are being multiplied by each other, or if they are being divided by each other, then how do we find the derivatives of such functions? That's the main topic. Those two are the main topics in this section. So as you can see here, for example, this is the product rule, and I might as well name this. So this is the product rule, which says that if two functions are being multiplied by each other and we want to take the derivative of such operation, that is equal, the derivative of such combination is equal to the derivative of the first function, let's call it f in this case, function f, the derivative of function f multiplied by the same function as g, and then plus the original function f, or the first function, times the derivative of the second function. In other words, the derivative of the first function times the second function plus the derivative of the second function times the first function. That's called the product rule. The quotient rule works, of course, a little bit differently. If you have two functions that are being divided and you want to take the derivative of such operation, the result is the derivative of the function in the numerator, or f prime of x in this case, times the function in the denominator, minus the derivative of the function in the denominator, or g prime x, times the function in the numerator, divided by the square of the function in the denominator. And that is called, of course, the quotient rule. Now, the derivatives of trigonometric functions are something that we also need to remember. So please make sure that you remember these operations. It may take you 10, 15 minutes to memorize this, but it's well worth your time because it's going to help you tremendously as we look at examples next. So next, the derivatives of a few trigonometric functions. So let's look at those. Now, here I use the prime notation for finding the derivatives. Now I'm going to switch to the other notation for finding a derivative because we need to be familiar with both of those. So suppose if we want to take the derivative of, so dx of function sine of x, right? A few times we've dealt with the derivative of sine of x, so that is equal to cosine of x and then next we want to take the derivative of cosine of x, which also we've seen before that this is equal to minus sine of x. By the way, I might as well mention at this point, it's extremely useful for those of you who will be taking higher calculus classes all the way to differential equations, that a notation like this is very, very useful. I mean, it's different, of course, from this prime notation, but what you can do with this dx notation is extremely useful because this, in other words, you can rewrite this as derivative of sine of x equals cosine of x times dx, cosine x dx. So this denominator, you can multiply both sides by it. And you can rewrite this expression in this way. And this is extremely useful beginning calculus 2. where you will see taking the integral of derivatives, that notation becomes enormously helpful and even necessary in that course, Calculus 2. And by the same token, you can rewrite this as derivative of cosine of x is equal to minus sine of x dx. So this dx, you can multiply both sides by dx and you get this result. Again, this notation is very useful in Calculus 2. Okay, so other derivatives of trigonometric functions are as follows. If you want to take the derivative of, let's say, tangent of x function, that is equal to the secant squared x. And by the same token, you can rewrite this as derivative of the tangent of x function is equal to secant squared x dx. Again, multiplying both sides by dx in this case. And other derivatives of trigonometric functions, suppose we want to take the derivative of cotangent of x. So since we took the derivative of the tangent, so let's also show the derivative of the cotangent function. That is, of course, equal to minus cosecant squared of x. Or in other words, we can practice for Calculus 2 and write this as a derivative of cotangent of x is equal to minus cosecant squared x dx. Okay? And then what else do we have? We have the derivative of the secant function, secant of x, which is equal to secant x tangent x function. And of course, we can rewrite this as derivative of the secant function is equal to secant x tangent x dx. Okay, and let me try to squeeze one last trigonometric formula underneath this. So we have derivative of, we talked about secant. Let's also talk about the derivative of the cosecant function, like that. And that is equal to minus cosecant of x cotangent x. So notice in particular which one of these have a negative sign associated with them. That would be for the derivative of the cosine, the derivative of the cotangent, right? Since we have to memorize these, let's find a way to quickly memorize them, and also the for the cosecant one. So this would be that one. And of course, you can rewrite this. I'm running out of space here, but you can, so I'm going to leave this one out, but you can rewrite this last one in the same way as these with the dx at the end of that, the right-hand side. Okay? All right. So let's apply these techniques to solving derivative kind problems. Suppose we want to differentiate the following functions. So differentiate each of the following functions. Okay, so here's one. We want to differentiate the function f of x equals square root of x times sine of x, right? So we have two functions that are being multiplied, and we want to find the derivative of this. Okay, so first of all, I want to rewrite this in terms of a rational exponent. So because it's easier that way to find the derivative of square root of x. So instead of square root of x, I'm going to write x to 1/2 power times sine of x. So these two are being multiplied by each other. Okay. So this is just rewriting the original function, and then of course we have the f prime of x. So first let's find the derivative of, of this first function, which would be 1/2 times x, 1/2 minus 1, which would be minus 1/2. All of that times the second function, plus the derivative of the second function times the first function. So that would be cosine x times x to 1/2 power, right? So let's clean this up because we have negative power here. We have, so let's clean this up so it looks neat and nice. So we have f prime of x. We're going to write this with positive power. So 1/2 is in the denominator. Let's move this to the denominator and write it in terms of a square root. So square root of x times, so this, all of that times sine of x. And of course, this is plus cosine of x times square root of x, right? Like that. So we can, I guess I can improve on this also. So f prime of x would be equal to sine of x, let's multiply, over 2 square root of x plus, and let's put this first, square root of x times cosine of x. So there we have the derivative of the original function there. Okay, let's do another example on this page. Suppose if we wanted to find the derivative of this function, y equals 2 secant of x minus cosecant of x. Okay, so we had y, so now we have y prime. Secant of x has derivative secant x times tangent of x, right? Let's bring this back. So the derivative of the secant function is secant of x times tangent of x. So we have 2 secant of x tangent of x. Then the derivative of the cosecant of x, this is one of the ones that generates a negative derivative. So minus times minus, it would be positive, right? So let's take it step by step. Minus, and then the derivative of that would be minus cosecant of x cotangent of x, right? That's also here, right there. The last one, derivative of the cosecant of x is equal to minus cosecant of x times cotangent of x. Okay, so let's clean this up and simplify it. We have y prime equals 2 secant of x tangent of x. Minus times minus is positive cosecant x cotangent of x. Okay, so let's do an example. That was b, so this would have to be c. Suppose if we have j as a function j as a function of v, then v cubed minus 2v, v to negative 4 power plus v to negative 2 power. So why these letters, I don't know. I'm just using the notation that book uses. Generally, though, I think it's a good idea if you're familiar with more variables used in these exercises. So we just don't want to stick with using x and y all the time. Okay, so this is, let's bring back that page. So when we have two functions that are being multiplied by each other, so we take the derivative of one function, multiply it by the next function, plus the first function multiplied by the derivative of the second function, right? So let's do that. So first we want to take the derivative of this. So this is our first function, this is our second function. We have 3v squared, right? 3 in front. We learned in section 2.3 how to take the derivative of such power functions, right? Remember that? Minus 2 times the second function plus the derivative of the second function times the first function. Like that, right? I'm just using the rules we learned in section 2.3. So if you have any trouble following this, please refer back to section 2.3. Okay, so now let's distribute and simplify this. I'm just going to quickly double check this to make sure that everything is okay. And then of course we took the derivative of this function. We got to multiply it by the first function, right? That's how the rule works. So like that. So derivative of this times that, then plus derivative of that times this. And that's what we have. So I'm just going to FOIL these and combine the like terms and so on. So 3v squared times v to the negative 4, that would be 3v to negative 2 power, right? The powers get added because the bases are the same when we multiply. When we multiply with the same base variable, the powers get added. Minus 4 plus 2 is minus 2. And plus 3v squared times v to the negative 2. Negative 2 plus 2 is 0. So anything to 0 power is 1. So 1 times 3 is just 3. Then minus 2. So we're done with this. Now we move to minus 2. Minus 2 times v to the negative 4 power is minus 2. V to negative 4 power. Minus 2 times v to the negative 2 power is minus 2 times v to negative 2 power. So we're done with that. Let's move forward with the other one. And after I've done this, I'll just double check very quickly. So minus 4 v to the negative 5 times v to v cubed. The bases are v. We add the powers. So we have, this is actually minus. So let me, because of that, let me correct that with my thick marker here. So this is plus, but because of this minus, so we have minus and then 4 minus 5 plus 3 is minus 2. Minus times minus is positive. 4 times 2 is 8. V to the negative 5 plus 1, it'll be minus 4. So we're done with this. We move to negative 2v to negative 3 power times v cubed. We have minus 2 v negative 3 plus 3 is 0. Anything to 0 power is 1. 1 times negative 2 is just negative 2. Negative 2v to negative 3 power times negative 2v. So we have plus 4v. Negative 3 plus 1 is negative 2. Okay, so I'm just going to quickly double check this. This looks good so far. So far looks good. And I forgot to mention to please pause the video So remember, memorize these. We have no choice, guys. You know, as a mathematician, I hate to ask you to memorize these things, but sometimes we have no choice. We need to remember these. So memorize these rules and these trigonometric derivatives of trigonometric functions. And then repeatedly pause the video. Sorry for the microphone is making noise and I don't know why it's doing that. It's probably my sweater, I don't know. So let's combine anything with -2 power. So we have 3v to -2 power, that one, and this one. This is -2, that's 3, so we get 1v to -2 power. -4, that's 1 minus 4 is -3v to -2 power. And then plus another 4v to -2 power, that's 1. So v to -2 power. And then the constants 3 and -2 add up to 1, just plus 1. And then what else do we have? Powers to v to -4 power. We have 2 of them, -2 and +8. So that's +6 v to -4 power. So we can rewrite this and clean it up a little bit in the descending order of power. Of course, here would have the highest power because power of v here is 0, and then -2, -4 would be in the descending order of power. So we can rewrite this as, in a more organized way, as 1 plus v to -2 power plus 6 times v to -4 power. This is fine too. So this is fine, and this is just, the final answer is a little more organized. That's all. Okay. So please pause the video from this point forward, and then make sure that you find the derivatives on your own before you see the video on the solution for each example. So this would be part D, and we want to find the derivative of, so this would be a quotient rule, right? X cubed plus x minus 2. So let's remind ourselves what we need to do here. So if we want to take the derivative of a quotient, we take the derivative of the function in the numerator, multiply it by the function in the denominator, then minus the derivative of the function in the denominator times the function in the numerator, all of that divided by the square of the function in the denominator. So let's do that. So take the derivative of this, what would you get? Just 1, right? Times the derivative of the, the derivative of the numerator times the entire function in the denominator, so x cubed plus x minus 2, then minus the derivative of the function in the denominator, which would be 3x squared plus 1 times x plus 1, which is the function in the numerator, divided by all of that in the denominator squared, right? So it will be x cubed plus x minus 2 squared. So of course in the numerator we can do quite a bit to simplify. So let's do that. Let's distribute and then combine the like terms. We have y prime equals x cubed plus x minus 2. Then first I want to FOIL this, then I'm going to distribute this. So let's do this. 3x squared times x would be 3x cubed. 3x squared times 1 is 3x squared. Plus 1 times x is just x. Plus 1 times 1 is just 1, right? All of that divided by x cubed plus x minus 2 squared. Of course, we need to distribute this minus in front. We need to distribute that into everything that comes after it, right? So let's do that. That's all of that. Then let's distribute this. Minus times 3x cubed minus 1 times 3x squared minus times x minus times 1. All of that divided by x cubed plus x minus 2 squared. Okay, so y prime, or the derivative of the y function, so we have two x cubed terms. We combine the coefficients. 1 minus 3 is minus 2x cubed. Then we have only one, only one x squared term, so minus 3x squared. And then, of course, the minus x and plus x cancel out. They add up to 0, right? Minus 2 minus 1 is minus 3. All of that divided by that x cubed plus x minus 2 squared. I mean, we can leave it like that, or we can do a little more simplifying by factoring out the negative here. Negative, negative, negative. Let's put that factor -1 and put that minus in front. So, so from here, we say y prime is equal to minus, that's that -1 factored out, 2x cubed plus 3x squared plus 3. All of that divided by that denominator. Like that. So these minuses got factored out here. Okay, important to remember to do that. All right. I hope you paused the video before you saw my solution for this. That way you'll learn this stuff much, much faster. So let's see. So this would be page 4. So that was, I believe, D. So this will be E, example E, and we want to differentiate or find the derivative of this trigonometric function. Okay, so remember the quotient rule, which says to find the derivative of a quotient, we take the derivative of what's in the numerator, that's f prime of x, multiply it by what's in the denominator, that's g of x, and then subtract minus the derivative of what's in the denominator, g prime of x, times the function in the numerator. All of that divided by the function in the denominator squared. So let's do that. So we have y prime, that is equal to derivative of cosine of x is, of course, minus sine of x, right? Right there we have cosine of x. The derivative of cosine of x is minus sine of x. Multiply it by the expression in the denominator. Then subtract that from the derivative of the denominator, which would be sine of x, it would be cosine of x, right? Derivative of sine of x is cosine of x, but let's remember that there's a minus here, so it would be minus cosine of x, right? That's the derivative minus cosine of x. What you see in the parentheses is the derivative of the denominator times, and this minus is part of the formula, remember? Minus, that's that minus, and then g prime of x, in our case, is minus cosine of x, of course, times the function in the numerator, which is cosine of x. All of that divided by that, 1 minus sine of x squared. Okay, so, or the parentheses, maybe this should have been parentheses, like that. Like that. Okay, so let's distribute and simplify this. That's easy to do. Minus sine of x times 1 is minus sine of x. Minus sine of x times minus sine of x is positive sine squared x. Then minus times minus is positive cosine squared x. Right? So, and all of that, of course, divided by 1 minus sine of x squared. Now, of course, recall from trigonometry, math 127, that cosine squared x plus sine squared x, or sine squared x plus cosine squared x, is equal to 1, right? It's a very useful identity or formula that we learned in trigonometry. That is true. So therefore, that helps us reduce what's in the numerator to 1 minus sine of x. So therefore, y prime would be minus sine of x plus 1 divided by 1 minus sine of x squared. And then, of course, visually scan this. This, if we rewrite it and say instead of minus sine of x plus 1, 1 minus sine of x divided by 1 minus sine of x, all of a sudden you notice that, okay, we can simplify things here even more. So let's do that. So all of this cancels with one of this, and we have, of course, 1 minus sine of x times 1 minus sine of x, again, because of this power. So we end up with y prime equals 1 divided by 1 minus sine of x. Like that. Okay. All right, so let's do another example. Please pause the video as you do these things. I'm sure you'll see the difference if you do that. You'll learn very, very fast that way. Okay, so this one, that one was E, so this one will be F. So we want to find the derivative of y equals 1 minus secant of x divided by tangent of x. All right? Okay, so the quotient rule would be find the derivative of this, multiply it by this. Then say minus, find the derivative of this, multiply by that. Then divide all of that by square of this tangent x. Okay, so let's do that. So y prime, the derivative of this one would be secant of x, tangent of x, right? So, but of course, because of this minus, we'll have to take that into account. So so secant of x, right there, you have the derivative of secant of x is secant x times tangent x. But we have this minus in front, so that's going to be minus secant x tangent of x. Times the function in the denominator, minus, of course, then the derivative of tangent of x. That was what? That one was, the derivative of the tangent of x is secant squared x times the function in the numerator. And of course, all of that divided by tangent x squared, like that. Okay. So I'm just going to quickly check this. It looks good. Okay, so that's okay. So let us distribute things in order to simplify these. So we have minus secant x times tangent squared x, right? Because of these two. And then minus, let's distribute this, minus secant squared x times 1 is minus secant squared x. Minus secant squared x times minus secant x is plus secant cubed x. Okay, all of that divided by tangent of x squared. Okay, then let's see what we can do here. We can factor out the secant x, right, from all of these. So let's do that. So y prime is equal to secant of x times minus tangent squared x minus secant x plus secant squared x. All of that divided by tangent x squared. Okay. So something interesting happens here, because check these two out. The secant squared x and minus tangent squared x. What do we know about these two from trigonometry? So recall, my ink is drying on that one. So recall from Math 127 that what did we know about the relationship between those two? We know that tangent squared x plus 1 was equal to secant squared x, right? We know that. But this is secant squared x and minus tangent squared x. So what is that equal to? We can use this equation to find that out. So using this, just rearrange these terms, move the tangent squared x to the other side, it becomes negative. So we have 1 equals secant squared x minus tangent squared x. So secant squared x minus tangent squared x, which is this arrangement, is equal to 1. So let's simplify that. So we have, so from that, we have that y prime is equal to secant x times, those two are equivalent to 1. So 1 minus secant x. You know, I too do forget these things. So if you forget them, don't worry about it. But develop a mechanism for looking back. So maybe you want to look back at your textbook for Math 127 and make a couple of sheets, make a list of these useful formulas. We had one earlier too, this cosine, this one. Sine squared x plus cosine squared x equals 1. There are a bunch of these from Math 127. So gather those on maybe a sheet, maybe a sheet and a half, so you can refer back to them in this calculus course. They make life, as you can see, they make life a lot easier, right? If we can simplify that expression to that, I mean, look at that. how much more simpler this is than that. Those two terms are gone. Instead, we have one. So it's really helpful. Like I say, I too do forget these, but it's nice to have a way of referring back to them. Okay, so now we have this over, of course, tangent x, or let me, so that's tangent squared x, right? So I think we can, yeah, we can leave it as that. So this would be our final answer here, like that. Okay. Okay, so let's do another example. Again, I hope you're pausing the video repeatedly, working these out on your own scratch paper, and then comparing your solution with mine. Okay, so that was E, right? That was F. So so this would be G, and then Y equals x squared. X squared sine of x tangent of x. So this is certainly an example where we can apply the product rule, right? So it is very helpful if we do, if we pair these up. In other words, let's rewrite this. So we rewrite this in this way. Y equals, or if you don't want to write it this way, but think of them like this. X squared times sine of x times tangent of x. So if you don't do this on a paper, then think of it this way in your mind. Separate this from this. Why do I say this? It's because then the product rule all of a sudden makes more sense and it becomes easier to apply. So you have, if you have two groups that are being multiplied, two functions that are being multiplied, and then you take the derivative of the first one, multiply by the second function, plus the derivative of the second function times the first function. So by doing that, now it's easier to see what we need to do, right? We can simply take the derivative of the first one. Well, let's do it, right? So we have y prime, take the derivative of this, which is 2x, multiply it by all of that. Because if you think of this as three different functions, it would be confusing. So do it like this, either on paper or in your mind, and then complete the derivative for it. So that's the first step. Take the derivative of this, multiply it by that, all of that, which is what I've done, then take the derivative of this piece and multiply it by x squared. So the derivative of this, it would be sine of x would be cosine of x times tangent of x. So this is a product within a product. Plus cosine of x times tangent of x. Then take the derivative of this, which is secant squared x, times sine, and then multiply by sine of x. All of that times, of course, x squared. So I hope you see that we've applied the product rule here twice. One time we did it to this, just these two, which is that. The second time we applied it to the whole thing. Okay, so that's what we applied the product rule twice. So now let us distribute and simplify. So we have 2x sine of x, that one, tangent of x, and then let's distribute this in x squared into this, so plus x squared cosine of x tangent x plus x squared, like that. Okay. So now, is there anything else we can do to simplify this? We sure can. If you look at this one, these ones, well, this one we can certainly simplify, right? So let's do that. So y prime is equal to, let me put this with the highest power first. So I'm going to move this and put it first because it has, the terms have highest power. So I want to organize this. And I'm going to put this last, and this one has a x to a higher power. So I'm going to go this, this, and then that. So x squared, secant squared x, sine of x, then this one. But I want to rewrite it so we can simplify it. So plus x squared times cosine of x, and now tangent of x, back from math 127, we remember that that is equal to sine of x divided by cosine of x, right? And then that one, which has, where I'm putting this last because the terms have the lowest power. Okay, that's all. And 2x sine of x tangent of x. So just like when we had, remember when we were dealing with quadratic functions, what did we do? We first put the term with the highest power first, then the next one with the lower power, and then plus maybe the constant like that. So that's what I'm doing, from higher power to lower powers. And so now you can see that we can cancel this cosine and that cosine. So the final answer would be y prime equals x squared secant squared x sine x, and plus x squared times sine of x, right? That's a much better expression than that one, right? This one as opposed to that one. So so we simplified that one to this, and now this, okay? And then, of course, the last one we can write as is, like that. Okay. So we'll leave it like that. So let's do another, maybe a couple of examples, but these will be different types of examples. So that'll be a nice change. So here we want to find an equation of the tangent line to the curve. That. So we want to do that for this curve, square root of x divided by x plus 1, and then the point is 4, 0.4. Okay, so the equation of the tangent line, for that, the tangent line being a straight line, we need the slope, right? Remember from basic algebra, when we were finding the equation of a line, a straight line, we needed the slope and a single point, right? So we can do that here, but we need the slope. So we need to, because we need this slope, we need to find the derivative of this. So let's do that. So because we need the slope of the tangent line, we'll need to find the derivative of y. Because the derivative is going to give us what? We define derivative, right? It's going to give us the slope of the tangent line. Okay, so let's do that. And of course, we need to apply the quotient rule. So y prime. So this would be, let me actually, let me rewrite this. So y equals x2 1/2 power over x plus 1, right? Okay, so now take the derivative of the numerator. So it would be 1/2 times x to minus 1/2 power times the expression in the denominator minus the derivative of the denominator, which is 1, times the numerator. All of that divided by x plus 1 squared. So let's simplify here. What do we have? We have y prime. We have y prime equals 1 over 2 square root of x, right? That's what that is. Times x plus 1 minus square root of x, of course. All of that divided by x plus 1 squared. So let's find the common denominator here, which would be 2 square root of x, so because we have a complex fraction here. So y prime would be equal to 2 square root of x, taking the, let me move this up. Move this up a little bit, like that. Because we're going to need to take the common denominator between this and that. So then we have, of course, x plus 1 minus square root of x times that would be minus 2x, like that. And all of that would be divided by x plus 1 squared. Okay. All right, so simplify this. So minus 2x plus x is just minus x plus 1. At the same time, let's simplify this. So 2 square root of x times the denominator. Like that. If you guys remember what we talked about, the easiest way to simplify a complex fraction is, so the denominator in this one is 1. Multiply the farthest terms. That would be these and these guys. Multiply them and put them in the numerator. That's what I did. Minus 2x plus x was minus x plus 1. Times 1, I got minus x plus 1. Then multiply the nearest terms in the complex fraction and put them in the denominator. So 2 square root of x times x plus 1 squared. It's a quick way of simplifying complex fractions. Okay, so this is the derivative. Now we need to plug in here. So this being the derivative. Now we need to find the slope by plugging in 4 for x. Okay, so let's do that. So finding the slope, we have the following. So y prime minus, just put in 4 wherever you see x. minus 4 plus 1 divided by 2 square root of 4 times 4 plus 1 square, right? So if we then simplify this, what do we get? We get, I'm running out of space here, but it's okay. So y prime is equal to, that's minus 3. And then we have divided by, square root of 4 is 2. 2 times 2 is 4, right? 4 times, this is 5 squared is 25, right? 4 plus 1, 5. 5 squared is 25 times 4 would be 100. So, in other words, the slope, so slope, or m, would be minus 3, minus 0.03. Okay? Now, we can find the equation of the tangent line by, so let me bring this up here. Okay, so recall that y minus y1 equals m times x minus x1, right? And we're finding this equation at this point. Point 4. And we found the slope, which is minus 0.03. So let's plug in. Y minus 0.4 equals m, which is minus 0.03 times x minus x1, which is 4. So rearrange all of this, we get, what do we get? We get minus 4 equals minus 0.03x. Minus 0.03 times minus 4, it would be plus 0.12, right? Let's, I'm not sure, so let me double check just to be sure. 0.03 times 4, 0.1, yeah, 0.12. And of course, we want to move this to the other side. And so we have y equals minus 0.03x plus 0.12 plus 0.4. This is maybe too many details, huh? You probably, I hope you don't get bored, but I wonder sometimes if I should skip steps or not. But anyway, so that plus 0.52. So here's the equation of the tangent line to that curve that we had, to this curve. My apologies. I think it's my sweater that is causing the microphone to do that, so to make that noise. I don't know if this is being captured in the video. I'm pretty sure it is, and so I think I probably should change to a different clothing that wouldn't do that. Okay, so let's do another type of example like what we did now. So this time, we have y equals x plus tangent of x, and the point is pi comma pi. Okay. So let's find the derivative of this first. Y prime is equal to 1 plus secant squared x, right? Secant squared x, and then So secant squared from Math 127, we remember that it is equal to 1 plus 1 over cosine squared x, right? There's a relationship between cosine and secant. The secant function is the inverse of the cosine function, right? The reciprocal. The secant function is the reciprocal of the cosine function. Okay, so now let's calculate the slope by plugging in the pi for x. So we have y prime is equal to 1 plus cosine squared of pi. We know that cosine of pi, we know from Math 127, cosine of pi is minus 1. So minus 1 squared would be 1. But let's take it step by step. So 1 plus 1 over minus 1 squared. So we have, so y prime is 1 plus 1 or equals 2. So this is the slope of the tangent line. Right, so just like before, we have, let's recall this from basic algebra. And the slope in here is 2. And the point that the tangent line goes through is pi comma pi. So let's plug in and find the equation of the tangent line. So y minus pi equals 2 times x minus pi. So we have y minus pi equals 2x. 2 times minus pi is minus 2 pi. Then y equals 2x minus 2 pi. Move this minus pi to the other side. It becomes positive pi. Y equals 2x minus pi. Minus pi. Okay? And that is the equation of the tangent line once again. Okay, so let's do one more example of yet another type. Okay, so let's see, so this will be page 9. So we have, so suppose that f prime or f of pi over 3 is equal to 4, and f prime of pi over 3 is equal to negative 2. And also, let us assume that the function g of x, let's assume that there is a function g of x that is equal to f of x times sine of x. And let's say h of x, function h of x, is equal to cosine of x divided by f of x. Okay? We may not have to use all this in this example, but this is what we have. Then we want to find g prime at pi over 3. We want to find this. Well, g of x, we're looking for g prime, right? So g of x is a product of two functions, f of x times sine of x. So let's find g of x, g prime of x first. So we'll have g prime of x is equal to f prime of x times sine of x plus derivative of sine of x, which is cosine of x, times f of x. Or I really didn't need these parentheses, but anyway, they're there. I drew them. But cosine of x times f of x. Okay, so all of this, so this is the derivative of g, function g. So this is g prime. And we want to evaluate this expression at pi over 3. So g prime at pi over 3 is equal to f prime at pi over 3 times sine of pi over 3 plus cosine of pi over 3 times f at pi over 3. Okay? All right. So this is where all those quantities that we were given is going to come handy here, because f prime, so let me write this below so we can have them. So f prime or f pi over 3 is equal to 4. So this is equal to 4. And f prime of pi over 3 is equal to negative 2. So this is equal to negative 2. Now, what do we know from Math 127 about these two guys? We know that sine of pi over 3 is equal to square root of 3 over 2, and cosine of pi over 3 is equal to 1/2, right? We know that from before. So let's multiply those. So g prime at pi over 3 is equal to minus 2 times square root of 3 over 2 plus 1/2 times 4. So we have minus square root of 3, right? The 2's cancel out. We end up with minus square root of 3, and half times 4 is plus 2. So I wanted to do one such example just in case when you work out the problems on the worksheets or the homework assignments, you have an example to go by here. Well, we've come to the end of another section here, and I thank you for watching the video until the end. And please remember to pause the video repeatedly before you see my solutions. Take the time to solve all of these examples on a piece of scratch paper before you see my solutions. So for now, have a nice day, and I'll see you again next time.